Hi, Haley. Hi, Dr. Tran.
Hey, how's it going?
Good. How about yourself?
Good, good.
How many classes do you teach in a row?
Uh, no more than two. So I have two on Mondays and Wednesdays, then two on Tuesdays and Thursdays. So it's kind of nicely balanced for me.
That's kind of nice. Yeah, because I have three class. So I have one class before this, and then your two classes. And I
Oh
just think,
man.
like, how do you do that?
Well, I mean, I prepare for it throughout the day, so so you get used to it. But I think teaching is it's a different kind of energy than kind of sitting in a class um,
Definitely.
because like when you're teaching, it's a lot more active. So I don't get bored, that's for sure. Yeah. Yeah, Houston. So to answer your question, yeah, we're basically assuming all isotropic materials right now, and so that's why we're able to use just a single value for like the Young's modulus, and we'll see today too. We're going to use a single value. We're going to bring the moment of inertia into the equation too. So for anisotropic materials, you're going to have different strengths and different directions, and so you can do that in ANSYS too. And so I do have a handout prepared for that, but I think probably we'll talk about it later in the semester when it becomes more relevant. Yeah, last year when I taught the class, there was a few people really interested in it because it's a big deal if you're running finite element simulations of 3D printed parts. Because with 3D printed parts, it's a lot stronger in certain directions, except for the one that you kind of printed it, because those are kind of layered on top of each other. So if you're doing something like that for your final project, and anisotropic material would be something good to use for that. So, but I have handouts and stuff prepared later in the semester for it. Inertia relief. Not explicitly in the class, but if that's something you want to explore in your final project, then we can talk about it then. I'm not quite sure exactly what that is and how to simulate that in ANSYS, but I'd be happy to look that up for you and kind of work with you on your project if that's something you want to do. Yeah, every time I teach this class, I end up learning something new about ANSYS just because you guys bring such creative and interesting problems to to do for the final project that a lot of times I have to do a little bit of research on my own on how to best simulate those things. So once we get to that point, definitely don't be afraid to kind of push the limits of what we can do. Okay, great. Yeah, usually for design for senior design projects, I end up working just kind of closely together with a lot of those groups because a lot of you guys have really interesting problems like that. So so that's pretty common. So once we get to that point, I'll be working together with a lot of you guys on that. Okay, so it's 4 o'clock, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today?
Doing well.
Good.
Yeah, doing all right.
Good. Yeah, it's the end of the week again, or at least end of the week for me. So after this, I just have one more class and then I'm done. So it was a short week, but it still didn't feel that short of a week. If you kind of know what I mean. Okay. So today we're going to be continuing on with our lecture notes on beams. So I think we just kind of barely started on it last time, and so today, we'll really get through it, and we'll do a couple examples and all that stuff. Okay? And so what you'll see from beams is that, at least in terms of how we do the problems, the method's still going to be the same. So we're going to start with, element stiffness matrices. We're going to assemble them, apply boundary conditions, and then solve. The only difference here is that, the element stiffness matrices are going to look different because our modes of deformation are going to be different. Okay. And so, this week and, next week, once we start getting frames, you'll probably start getting tired of this entire process of element stiffness matrices and stuff. But the reason I kind of hammer it home at this point in the class, because, even though direct stiffness exactly is not what like ANSYS uses, this whole process of doing element stiffness matrices in assembly, all of this is done by ANSYS and all kinds of finite element software too. So, getting, the specifics of, what the element stiffness matrices look like, it's less important to me that you kind of remembered that. But what I want you guys to get from this section of the class, basically all the way up until the first midterm, is just this kind of general process through which, a finite element analysis is conducted. Okay. Oh, question. What did I cook this week? Actually, I did make something interesting a couple nights ago. So there's this Asian condiment known as XO sauce. So it's basically a sauce made with a bunch of dried seafood, actually. So it uses dried scallops and dried shrimp. And so my fiance and I, we really like that sauce. We basically put it on everything. So I made a batch of that stuff because normally if you buy it in the store, it's like $15 for like a kind of a tiny jar like this. But if you make it homemade, you can spend the same amount of money with a larger amount of sauce. Yeah. Okay. So are there any questions on, so I know we have the homework is going to be due next Tuesday. So it's fairly soon. And it's a fairly large homework too. So definitely make sure you're working on that. Are there any questions on the, are there any questions on the homework that I can answer before we get started? Okay. All right. So just kind of as a side note too. So I showed my friends some of the memes that you guys make, and like they basically they're all fans too. So they said whenever I show them a meme that you guys make, they say, your students are awesome. And I said, yeah, they are. They're very creative and they come up with really great memes. So definitely keep them coming because it helps a lot. Okay. All right. So let's continue on with beams. Okay. right? All right. The idea with beams, remember, so we've basically just gotten done talking about springs and truss elements, right? And so to kind of refresh your memory, springs and trusses, they kind of look like this, right? And so we have kind of a slender element like this, and then trusses and springs are known for deforming like this. Okay, and I'll draw a second arrow there. Right? And so they're only known for displacing what's called axially, which is down the length of the beam. Okay, and so what results from that is that truss elements are either in tension or they're being pulled apart or compression. Okay. And truss elements, actually, you can make a lot of really complex structures with that too. And I remember, like when I first learned statics, we spent a lot of time with trusses because those are generally you want for a stable structure, you want things to be in tension and compression because that's what ends up being most stable, right? But in reality, things don't always end up like that, and you end up with these elements that are loaded and deformed differently. Okay, and so if we consider a beam element, which to kind of make it different, I guess I'll draw it as a rectangle. Okay. And so in a beam element, we're actually considering what I like to think of as the other two modes of deformation. Right? And so we have one mode of deformation that goes like this. Okay. Right. So they don't necessarily have to be up, but they're basically up and down. And so these are, you can think of them as perpendicular to kind of the axis of the element. Okay. Right. And since these are going to be in the y direction, I'll call these, u1y and u2y, okay? And of course, these are hats because they're local to that element, okay? And then in addition to this, we can also consider rotations. Okay? Okay. And so that's basically just to denote how an angle can be kind of or an element can be kind of twisted and change its orientation, right? And so you can think of such cases where maybe this left end of the beam right here, maybe it's not moving, but it's kind of twisted in a certain way based on how it's loaded. Okay, and so these are two modes of deformation that we haven't considered yet because they're not part of the truss equations. Okay, and so an element that can support these two deformations are known as beams. Okay. And then just to kind of label these and to kind of give them names, these deformations that are perpendicular to the axis of the beam, we call these transverse displacements. Okay? Okay. So these are transverse displacements. And then in the green right here, which are our rotation, these are our rotations. Okay. All right. And so since we're supporting, different modes of deformation, that means we're going to have a different element stiffness matrix. Okay. And so let me redraw the beam one more time. Because what I've shown you up on the middle right here in the red and the green, these are the deformations. But remember, in finite elements, we always have to have a relationship between deformations and the corresponding forces. Okay, and so the corresponding forces for these guys would be, they're going to go in the same direction, and so we're going to have F1y, F2y. Right, so these F1y and F2y, these are transverse forces that you can think of as being applied at the ends of the beam, which are going to cause transverse displacements. Okay. And then to cause a rotation, the way that we do this is we apply a moment, and so that's M1 and M2. Okay. Okay. And so what we're going to show next is the element stiffness matrix for these guys that relates these nodal forces and nodal moments to their displacements. Okay. All right, any questions on this so far? Oops. Okay. All right, so the element stiffness matrix for these, for these elements are based on, the beam equations, okay? And so that's the Euler-Bernoulli beam equations. Okay? Right, so the equation for that is actually a fourth order differential equation. Right, so these are the beam equations, and so to derive the element stiffness matrix, basically is we're going, the derivation kind of follows this, and so the details for that are in the notes. But I think just for this class, I think we'll just skip to the end, and I'll just show you the element stiffness matrix so we can use it in problems. Oh, going back, yes, I can do that. Okay. And so if you're interested in seeing the element stiffness matrix, that's or the derivation for that, it's in the notes. But for this class, we're just going to skip to the end. Okay. All right. So our element stiffness matrix in this case is going to be a 4x4 because we have actually 4 degrees of freedom here. Okay. Right. And so what I mean by degrees of freedom is those are basically the number of unknowns that we're solving for in the for each element. Okay. Because for each element here, we're solving for both the transverse displacement, so that's 2 degrees of freedom, and also the rotations, and so that's another 2. Okay. All right. So the 4 degrees of freedom are u1y, u2y, is theta 1, theta 2. Okay. Right, and so our element stiffness matrix looks like this. So we're going to have F1, Y, M1, F2, Y, M2, okay? And the forces have hats on them, okay? Because they're in the local coordinate system. Right? And then the element stiffness matrix is given by the following. So first, out in front, we have our coefficient, and so we're going to have EI for L cubed. Okay. And I'll define all those parameters in a second. Okay. But let me write in the element stiffness matrix first. We're going to have 12, and then 6L, and then minus 12, 6L. Okay. And then we have 6L, 4L squared, minus 6L, 2L squared, okay, minus 12, minus 6L, 12, and minus 6L, 6L, 2L squared, minus 6L, and 4L squared. Okay, and these are multiplied by the nodal degrees of freedom. So we're going to have U1y, theta 1, U2y, and theta 2.
Where did you get the values again? Was that on the previous page? I think I kind of missed it.
The values for in this matrix.
Yeah, yeah.
So there's kind of a lengthy derivation for this. So I'm basically skipping it for this class because it's
You're just giving us the matrix.
Yeah. So it's a little bit involved, and I think it kind of distracts from kind of the overall picture. So I do it for my graduate students because I think it's to derive this, I think, is important for them. But for this class, I think let's just work with this element stiffness matrix here. Yeah. Mm-hmm. Yeah. So question in the chat. So there's no hats on the moments due to it being horizontal. Yeah. So actually, the moments are kind of independent of the coordinate system, and so that's why you don't see any hats on the thetas. And so if you think about it, if no matter if you're in one coordinate system or another, how you characterize the rotation is kind of the same, because remember, rotations are given in terms of angles, and so since angles don't have any units, there's really no need to convert them. Yeah. Mm-hmm. Okay, so let's go ahead and define the parameters here, right? So we have three of them here, right? So let's start with E, and so E is the same as before. So E is our Young's modulus. I here is our moment of inertia. Okay, and so that's the moment of inertia of a cross section of the beam. Okay, and then L here is simply just going to be the length of the element, or length of the beam. Okay. And so a lot of those things are either, very easily quantifiable, or, you can look them up in a table. Okay. And then once you have all of those things, you can put together the element stiffness matrix for a beam. Okay. All right. And so let me just write one more thing. So derivation in lecture notes. Right. So if you're interested, the lecture notes kind of has that full derivation, but for just for the lecture, I'm going to skip that here. Right. Okay. Any questions on this? Okay. All right. And so before we do an example, I want to talk about constraints again. So we spent a bit of time last lecture talking about constraints, but actually with the beam, where we now have this rotational element, we need to introduce a new kind of constraint. Okay. And so we actually are going to have three different kinds now. And so we're going to have one called a fixed support. Okay. And so visually, it looks like this. Okay. And so fixed support, the way that you kind of see it in a picture, is it literally looks like something is either welded to the wall, or it's bolted to a wall. Okay. And so a fixed support basically is the most constrained support that you can do, because it's going to restrict all elements of deformation. Okay. And so if we consider this to be like, node number 1 right here, and so node number 1 here is attached to the wall, all elements of displacement and the rotations are going to be 0 here. Okay. And so we have u1x, u1y, theta 1. Okay. All of these guys are going to be equal to 0 on a fixed support. Okay. And so fixed support is going to knock out all of these. And so, if you have a problem where, you have a fixed support, you're going to apply a Dirichlet boundary condition on all three of those displacements. Okay. Right. And so, for the beams, we're only going to be working for now with the UYs and the thetas. And so that's the transverse displacements and the rotations. But next week, once we start getting into frame elements actually have all of these guys together. So frame elements have the X displacement, the Y displacement, and the theta. This is how you would basically treat a fixed support in that case. Okay. But I wanted to talk about it now just so, we're kind of ready to work with them in frame, because frames are a lot. Okay. So that's the fixed support. Next, we have the pin support. Right. So actually, these are the ones that we've kind of been working with mostly for our trusses. Okay. And so visually, it looks something like this. Okay. And so you can think of it almost as like your element is being pinned at that node. Okay. And so for a pin support is going to restrict the components of displacement, right? Right. And so for a pin, since it's being kind of pinned there, we can't displace at all. So u1x and u1y is equal to 0. But our rotation here is not going to be constrained, okay? Because the thing about a pin is that it's free to kind of rotate, right? And so if we pin it, then that's going to place no restriction on the rotation. Okay. And so when we go to do problems, for a pin support, we're not going to apply Dirichlet boundary condition on theta. Okay. And you'll kind of see how that works in the next problem. Right. And then the last support that we have is the roller support. Okay. And so this is the one that we talked about last time. And so it looks like a, like a roller skate or roller blade, okay? And the thing with the roller support is that it's only going to, just like we talked about, it's only going to knock out the displacement perpendicular to the surface, okay? And so in this case, since the surface is horizontal, what that means is that we're going to have u1y is going to be equal to 0, but u1x and theta 1, both of these guys are going to be free. Okay? And so they're going to be free to displace or rotate however much it wants. Okay. And that's what the wheels kind of represent. So the wheels kind of represent that it's kind of free to displace in that direction. And so when we're doing our finite element problems, and you come to the part where you apply your Dirichlet boundary conditions from the supports, make sure that you're knocking out the correct components based on the type of support there is in the problem. Okay. All right. Any questions on this before we do an example? Okay. All right. So let's do an example problem just to kind of see how this works in practice. Okay. So let's consider this this beam. It has two elements. Okay. All right, so on one end, we're going to have a fixed support, and that's our first beam. And our second beam is going to be connected just like that. Okay. And then on this end, we're going to have a pin support. Okay. All right, so let's go ahead and label the elements. And so this will be element A. This will be element B. Okay. On the left right here, we're going to label this node 1. In the middle, we'll call it node 2. And on the right side, we'll call this node 3. Okay. All right, so we have a 3-node system. And we're also going to have two forces that are going to be applied. Okay, so on the middle, we're going to have a vertical force of P. Okay. And then we're also going to apply a moment of M. Right, so it's a fairly simple beam. All right, so just for simplicity, we're going to assume both of the lengths of the beams are the same, so they're going to be of length L. And we're also going to assume that the Young's modulus and the moment of inertia are the same throughout the entire beam as well. Okay. And so just to kind of give an idea, so the point of this example is to kind of more show you how to assemble a global stiffness system with beams and how to apply boundary conditions. So there are no numbers here, and so what we're going to do in this problem is we're going to assemble or compute the global stiffness system. Okay. And so this is going to be after we apply the boundary conditions. Okay. Right. And so just because there aren't any numbers here doesn't mean we can't follow our same approach. And so we're going to do the same approach that we've always done. So we're going to start with the element stiffness matrices for elements A and B. Then we're going to put them together into one system, and then we're going to apply our boundary conditions. And so the only thing that we're not going to do is just plug in numbers and solve in MATLAB. Okay. Yep. So I is the moment of inertia. Yeah. Mm-hmm. Yeah, so the moment of inertia is going to depend on the shape of your the shape of the cross section, right? And so depending on if you have like a rectangular cross section or if you have an I-beam, okay? These shapes have different moments of inertia, and so typically, for this class, most of the time I would probably give you the moment of inertia, but for practical problems, if you're solving these, you would look at the shape and the dimensions of your cross section, and you would look up in a table on how to compute moment of inertia. Yeah. Mm-hmm. Okay, and so let's go ahead and start solving this problem. So our first step, anytime we do a finite element problem, is to write out the element stiffness matrices for all of our elements. Okay. Okay. And so in this case, the element stiffness matrices for A and B are going to be the same, right? Yeah. So this is a, hopefully it brings back memories from statics. Okay. Okay. And so we have KA and KB. Okay. So these are both going to be the same. So I'm only going to write it once. Okay. Right. So it's going to be EI over L cubed times 12, 6L minus 12, 6L, and then 6L, 4L squared, 6 minus 6L, 2L squared, okay, minus 12, minus 6L, 12, minus 6L, okay, 6L, 2L squared, minus 6L, and 4L squared. Okay. All right. And so multiplying this, we're going to have our nodal degrees of freedom. And so we're going to have U theta, U theta. Okay. And so the exact numbers for these are going to depend on which element that we're talking about. So for element A, these are going to be 1, 1, 2, 2, right? But for element B, element B acts on nodes 2 and 3. And so this is going to be 2y and 3y. Okay. And so remember, knowing which nodes that they work on are really important for the problems. Okay. All right. So now that we have the element stiffness matrices, we're ready to assemble them together into one system. Okay. So before we do that, are there any questions on this? Okay. All right. So the second step here is assembly. Okay. And so in assembly, we're going to put all these guys together into one matrix. Okay. Okay. And so our one matrix here is going to be 6 by 6 because we have 3 nodes. And at each of the 3 nodes, we have, one displacement and one rotation. Okay. And so out in front, we're going to have EI over L cubed. Right. And then we're going to have 6 columns here. So we're going to have U1Y, theta 1, U2Y, theta 2, U3Y, theta 3. Okay. Okay. And then those are all the rows. Okay. And then now let's go ahead and fill in this matrix. Okay. And so I'm going to use this red color to denote element A. So let's go ahead and box the all the degrees of freedom for element A. Okay. Okay. And so element A is going to take care of the 1, 2 block, and so that the 1, 2 block is given by that right there. Okay. Okay. And then element B is I'm going to write in green, and that's going to be this block right here. Okay. And so we have an overlap here on node number 2. Okay. All right.
For element B, does it start at U2Y?
Yeah, it starts at U2Y because it's element B works on node number 2. And so you're going to have U2Y and theta 2 for that one.
Okay,
Yeah.
thanks.
Mm-hmm. Okay, and so let's go ahead and fill in the entries for everything that's boxed here. Okay, so we're going to have 12, 6L, minus 12, 6L, then 6L, 4L squared, minus 6L, 2L squared. Okay. Then we have minus 12, minus 6L, right? And so starting here, we have an overlap. And so remember, whenever we have an overlap, we add those guys together. Okay. And
So we're just adding what you gave us, just the corners to each other. So we're doing it twice, but then we're
Exactly.
adding what overlaps.
Exactly.
Okay.
Right, right. And so in this overlap here, we have 12, which comes from, element A, and we also have a 12 that comes from element B. Okay. And so we're gonna have 12 plus 12. Okay. In this next spot, we're gonna have a minus 6L that comes from element A and a positive 6L that comes from element B. So both of those guys are gonna cancel out. Okay. Right, so same thing in this spot right here. So we have minus 6L plus 6L. Right, and then in that bottom right overlap spot, we have 4L squared plus 4L squared. Okay, and so that's going to end up being 8L squared. Right. Oh, so question. So for element stiffness for A, how come we choose Y and theta and not X and theta? Yeah, that's a good question. So the Y direction here, I kind of implicitly choose the Y direction to be perpendicular to the element, right? And so the element's going from left to right, and then the Y direction is going this way. Because for a beam, remember, we're considering displacements in that transverse direction. And so trusses are the only ones that have displacements in this direction, in the X direction. So for when we're doing beams, we're doing Y and theta. Yeah. Okay. Right, so then we have minus 12, 6L, minus 6L, 2L squared. Okay. Minus 12, minus 6L, 12, minus 6L. Right, and then 6L, 2L squared, minus 6L, and 4L squared. Okay. Okay. And so there's our, global stiffness system, right? And so, for everything that's overlapped, we can go ahead and add those up. But the reason I wanted to do this problem is, part of it was this, but the other part was applying our boundary conditions, okay? And so let's go back to our diagram on the previous page and see where we have to apply our boundary conditions, okay? All right. And so from the previous page, we see that we have, boundary conditions on node 1 here. And so, what we're going to do is we're going to, see what type of constraint this is, and then knock out the elements of displacement based on that constraint. Okay. All right. And so here, we have a fixed constraint, and so what that tells us is that all the aspects of of displacement are going to be 0 here. And so for this problem, this tells us that u1y is equal to 0 and theta 1 is equal to 0. Okay. Or in other words, we're gonna change the rows and columns that correspond to this one. Okay. And so if we go back to our global stiffness system, we see that the two rows that correspond to u1y and theta 1 are the first two. Okay. And so we're going to change these into all zeros and ones. Okay. And so once we do that, we end up with the following. Okay. And so that's our, our fixed support boundary condition. And then now let's look at the pin support boundary condition on node number 3. Okay. So node number 3, we have a pin. And so then for a pin, we're going to leave the rotations alone. And so we're not going to do anything to theta 3. But what it does tell us is that u3y is going to be equal to 0 here. Okay. And so let's go ahead and change the row for u3y, which is going to be this guy right here. Right. And then we're going to change this to all zeros except for 1 on the diagonal. Right. So we're going to have 1 here and then zeros everywhere else. Okay. And then of course, you know, you can go ahead and fill in zeros wherever it's not filled in. Okay. Oh, I think I forgot to fill in these two. So this is 6L and then 2L squared. I don't know if I erase them. Okay. And then we're also going to have 0, 0 right here. Okay. Yes, this is not a satisfying thing. It's tedious. And you know, I know that.
You sure you don't want to add any more boundary conditions?
I'm sure
Got any more to
for this
spare?
one. No, for this one we're good. We're good on boundary conditions for this one. Okay.
Let me
At
know if you
least,
change your mind.
at least this is it for the supports. But you know, we have to add our loads in. But our loads are simple, right? So for our loads, remember, we're just going to put those into the rows that they act. Okay. And so in this case, we have loads that act on node number 2. Okay. And so when we do our load vector here, okay, since we don't have any loads that are acting on nodes 1 and 3, we can just leave those empty. Okay. And then for the row that corresponds to U2y, since we have a force of negative P, we're going to put a negative P right here. Okay. And then for theta 2, we're applying a moment on that node. And so on that row, we're going to put an M right there. Okay. All right. And so at this point, you know, if we had numbers for this, we can go ahead and plug those in. But since we don't have any numbers, you know, this is kind of the end of the problem. And so, you know, we've accomplished our goal of setting up the linear system. Okay. All right. Any questions on this example? So I have a question for you guys, actually. So, you know, I guess someone's comment earlier is that this reminds them of stat. Is this how you guys learned statics, to basically set up systems of equations like this and solve it?
Yes, it's not in matrice form.
Okay.
Sorry, Sarah.
Yeah, that's what I was gonna say.
Okay, so you do set up all these equations similarly. So I kind of remember that from my statics class too, where we set up the equations, but we didn't solve it in a matrix like this. But this whole concept is kind of is familiar to you guys, right?
Yeah.
Okay.
Yeah, especially when it comes to the supports and stuff.
Okay.
Supports.
Okay, great. Yeah, maybe I'll skip the frame stuff then, because after this, the next thing actually is frames, where frames are kind of you know, all of this kind of on steroids. If believe it or not, this is not as bad as you can get, because for a frame, you know, you have all three, you know, elements of all three modes of displacement. So your element stiffness matrices for frames are actually 6 by 6. And so, you know, what we've drawn right here, you would write one of these out for just one element, and then you'd have to do that times however many elements you have in your system. So maybe for this class, maybe I'll skip the frame stuff, and then we'll kind of go to probably some more new stuff that you guys probably haven't seen. So I think probably that's probably better, because, you know, I think there's only so much of these you know, element stiffness matrices and beams and stuff that you can take before you go crazy. Okay. But I do want to finish the beam stuff, because you know, we've already kind of started this. And so let's talk about reaction forces next. Okay. So let's talk reaction forces. So and so just like, you know, just like we did for bars and springs, we can take our finite element solution and use that to compute the reaction forces at all the nodes. Okay. So after right? And so this is basically exactly the same as what we did on Tuesday, right? So if you remember on Tuesday, what we did was, after we solved for, you know, the X and Y displacements at all the nodes in our truss, what we did was we just kind of plugged it back into our, our element, our global stiffness system before we applied the boundary conditions in order to get the, the reaction forces. Okay. Okay. And so, in the previous problem, what we would do is after we solve for u1y, theta 1, u2y, theta 2, u3y, and theta 3, you would just simply plug this back into our global system, which was, the part, before we did all the zeroing out and before we did on the right-hand side. Okay. And so for the previous problem, we would do something like this. Okay. Out in front, we have EI over L cubed. Right. And so after we solve for, u1y, we plug in here. Right. Right. So our global stiffness system looked like this. Right. So it's 6L, 4L squared, 6L, 2L squared, 0, 0. And then 0, 0, 0, 0, minus 12, minus 6L, 12, minus 6L, 6L, okay. And so to this, we're going to multiply u1y, theta 1, u2y, theta 2, u3y, theta 3, okay? And so at this point, remember, this is after we solve the finite element problem. So all of these guys here are known, okay? And so you just have to simply plug those in, okay? And then once you get after performing this matrix vector multiplication, is you're going to get all the reaction forces at all the nodes, okay? And so again, with these kinds of complex, and tedious matrix calculations, don't be afraid to use MATLAB for these, because that's what MATLAB was built for. And so if you can perform this matrix vector multiplication in MATLAB, that's going to help you out a lot. Okay. Okay. And so just like we did before, after you compute these forces, it's usually good to perform a quick sanity check, right? And so you should check to see whether some entries are 0 or not. All right. And so generally what you should get is, you should get values that are non-zero in 2 situations. Okay. All right, so this is sanity checks for reaction forces. Okay. All right, so you should get non-zero values in situations where either one, you have a support on that node. Okay. Okay. No question? Oh. No, we're not playing Mantras of Madness. This is just for just for checking your answer, just to make sure that makes sense. Okay. And so the if you have basically a node that's supported, and so if we go back to our previous example here, we say that let's take node 1 for instance. So in node 1 we have a fixed support, And so what you should get when you compute the reaction forces, you should get a non-zero reaction force at node 1, okay? A non-zero reaction force and a non-zero moment, because those are forces that the support is applying onto your structure to make sure that it's in static equilibrium, basically, okay? And same thing for node number 3. So node number 3, we have a support, but the support is only on the displacement, right? And so we only have a support that constrains U3Y, okay? And so what that tells us is that, you know, the reaction force in the Y direction at node 3 should be non-zero because, you know, it's supporting the structure there. But M3 actually should be 0 because there's nothing constraining it in the M3 direction, okay? Right. And so after you compute your reaction forces, definitely check the results at the constraints. You know, whichever nodes are supported, just to make sure that you get, you know, values that are non-zero that should be non-zero. Okay. All right. And so the other case where you get a non-zero value is if you have a load that's being applied on that node. Okay. Okay. And so in fact, you know, the reaction force that you compute on the loaded node should equal exactly the load that you're applying. Okay. And so if we go back to our example here, if we computed the reaction forces and reaction moments at node 2 on this example, right? The reaction force F2y, after you compute that, you should get exactly minus P. Okay, because that's what you're applying on there. And similarly, if you compute the reaction moment at node 2, you should get M because that's what we're directly applying, okay? And so those are the only two situations, you know, when you're computing reaction forces where you should get a non-zero number, okay? And there's also going to be cases where you get a zero value, okay? And so zero values are a zero reaction force basically means that there's no force being applied at that node. Okay. And so these are all nodes that are free, or all degrees of freedom that are free. That means they're not being supported and they're not being supported and not being loaded. Okay. Okay. And so if you don't have a support and you don't have a load, then you should get a zero reaction force at those nodes. Okay. Okay. Any questions on this before we do another example?
Can you explain again the non-zero value one support on node?
Yeah. So the basically what that basically says is that when you compute the reaction force, remember reaction forces are, you know, the actual forces that are felt on those nodes. Okay. What I mean by supports are the nodes that are having their degrees of freedom constrained. Okay. And so if we look at node number 1 right here, you know, it's a fixed support, right? So that means it's both its displacement and its rotation are being constrained. In fact, they're being set to 0, right? And so because of that, you know, there's going to be a force that the support applies onto the beam, basically in order to keep it in static equilibrium. And so whenever you have a support that kind of constrains some kind of movement, there should be a reaction force there that kind of prevents that specific movement.
Okay, thank you.
Mm-hmm. Okay. All right. And so let's take that information and let's apply that into another example. Okay. And so this example it's going to look very similar to the previous one, except it's going to have some numbers, but there's going to be one wrinkle to it. Okay. All right. All right. So just like before, we're going to have a beam that's going to be fixed on one side. I'm going to split this beam into 2. Let me label all the nodes here. Okay, so this is going to be node number 1, node number 2, node number 3. Okay, we'll call this element A and element B. Okay, but instead of a pin support on the right side, what I'm going to add instead is a spring. Okay. Okay. So now the spring is going to be, supporting that right side of the beam. Okay. And so this spring right here is going to be another element because it's an element that we've talked about before. So we'll call that element C. And we also need to label the node where it's fixed to the ground. So we'll call this node number 4. Okay. All right. So let's put some parameters on this guy. So the two beams, they both have the same length. Right, and that length is going to be 3 meters. Okay. And then, we're going to say that elements A and B have identical properties. And so they're going to have the same Young's modulus. And so this is for A and B. Okay. And so the Young's modulus of these beams is going to be 210 gigapascals. And then the moment of inertia is going to be 2 times 10 to the minus 4 meters to the 4th. Okay. And then for the spring, the material constant that we need is the spring constant. Okay. And so for element C, what we have is a spring constant K, which is going to be 200 kilonewtons per meter. Okay. And so the last thing we need before we start to solve this is a load. And so let's say that we're going to apply a load onto node 3 right here, and it's going to be vertical. Okay. And this load is going to have a magnitude of 50 kilonewtons. Okay. All right, and so we have a 3-element system here with 4 nodes. And so, just like we've done in all the previous problems, let's set up the finite element problem and solve for all the nodal displacements and rotations. And then after we do that, then we'll be able to compute the reaction forces and reaction moments. But we'll cross that bridge when we get there. Okay. All right. Any questions on the problem setup?
Dr. Tran,
Yep.
can we just make a simplification and just say A and B are the same thing and just say L is equal to 6?
You could, but you lose a little bit of detail there because if you the way it's set up right now, you can compute the displacement at the middle of the beam here at node 2. And so if you make this all one beam, you'll be able to compute the displacements. Well, I mean, at node 1, there's no displacement because it's fixed, and at the end at node 3. But it could be for your problem that you're interested in, what's the deformation at the middle of the beam right here. And so by splitting it up, we can actually compute that.
Gotcha.
Yeah.
Thank you.
If we cut both the elements like in half, would that just be more accurate?
Yep. Actually, yeah, that's actually my next point too. So cutting it just once is just arbitrary, right? But if you want more spatial resolution, you can keep cutting this beam up, just like that, right? And you can make like a nice candy necklace or something like that. But just remember that every time that you cut the beam in half, that's one more element stiffness matrix, and your global system's going to grow by that much too. And so it's it results in more accuracy. It just ends up being more work. Right? But it's a good concept to talk about because you did a little bit of this in your first ANSYS activity where if you remember, I had you try the simulation with different numbers of mesh elements, right? And so I had you try one with a mesh of 5 millimeters. Okay. Then I had you increase that mesh size to 10 millimeters, and you saw the mesh get more coarse. And then I had you try one with 2.5 millimeters, which made the mesh really, really tiny. Okay. And so the same concept applies there, right? So the more elements that you have, the nodes are going to be more packed together just because you have more elements. And so you end up with a result that's more accurate and you have a better spatial resolution, but it just ends up being more expensive just because you have more things to solve. Whereas a coarse mesh, it's a lot easier to solve because you have less less nodes, but it's you're not going to get as much accuracy or spatial resolution. Yeah. Mhm. Okay. All right. So let's go ahead. Let's go ahead and start solving the problem. And so the first step, just like in all of these problems, is the element stiffness matrices. Right. So this problem is interesting because we're kind of bringing together kind of both of our lecture notes on this. We have the beams, but also we have springs. Okay. All right. And so I'm not going to write out the full element stiffness matrices here, but I will write out what nodes that they act on, right? Because that's a bit more important here. So we're going to start with Ka, and so Ka is going to be Ei over L cubed. Okay. And so I'll let you guys fill this in if you want. Right. But I do want to write down what nodes that it acts on. So node or element A is going to be acting on nodes 1 and 2, and we also know that it's a beam element, and so it's going to be the degrees of freedom are going to be u1y for the transverse displacement, theta 1, u2y for the transverse displacement, and theta 2. Okay. Right. And so similarly, KB is going to be the same thing. But KB is going to be acting on nodes 2 and 3. And so this can be new 2y. Actually, I'll write KB on the next page just so we have more space. Okay. So before I do that, are there any questions on this? Okay. All right. So let's do KB. All right. So KB we have EI over L cubed, and once again we have all the tedious stuff. And then it's going to be acting on nodes 2 and 3. So we have u2y, theta 2, u3y, and theta 3. Okay. And so now we have the spring. Okay, so the spring is going to be by Kc. Okay. And so for the spring, we can write this out because it's just a 2 by 2. Okay. So remember, for a spring, our element stiffness matrix is just K minus K minus K and K. Right. And now we come to the part where we have to list out its degrees of freedom. Okay. So remember, the spring can only compress and stretch, right? So the spring can't handle any transverse displacements, right? So in other words, the spring can only displace this way and this way. So I mean, just by the nature of the force, we know that it's going to compress, okay? And so we have to kind of turn our heads a little bit because our spring here is vertical, right? Because normally when we say for a spring, we say that spring might look like this. We call this node 3 and 4, right? Normally we say that the degrees of freedom for the spring are going to be u3x and u4x, okay? That's what we would normally do. But in this case, since the spring is vertical, when you stretch the spring and it displaces axially, the direction is actually going to be y, right? And so the degrees of freedom that the spring acts on here are actually going to be u3y and u4y, right? Does that make sense why I chose y for those for the spring element there?
Yes, it does.
Okay, great, good. Okay, and so now that we have the element stiffness matrices, well, I mean, at least as much as we can tolerate writing, now we can go ahead and fill these in to the global stiffness system. And so our global system here will have an interesting number of rows and columns, right? Because normally, you know, for the previous beam problem that we did, for every node that we had 2 degrees of freedom, right? So we had a transverse displacement and a rotation, okay? And so in this particular problem, we have 4 nodes, okay? So we have nodes 1, 2, 3, and 4. And so since nodes 1, 2, and 3 are on the beam, you know, we're going to have transverse displacements and rotations at all of those nodes, okay? And so, so let's list out our degrees of freedom. Okay. And so first we're going to have U1y, theta 1. Okay. So both of these guys come from node 1. Okay. Then we have U2y, theta 2. Both of these guys come from node 2. Okay. Then we have U3y and theta 3, and so these guys come from node 3. Okay. And so since all those nodes are on the beam, you know, we need all of these degrees of freedom. Okay. And then finally we come to node 4. So node 4, you know, in the end it's not going to do anything because it's a fixed support. But you know, we do have to include it into our matrix. Okay. And so node 4 right here, since it's only attached to the spring, the only degree of freedom that we're going to get from node 4 is U, right? And so from node 4, we're only going to have U4y. Okay. Okay. And so the reason we don't have theta 4 is because, you know, the node 4 isn't attached to the beam. And so there's no way for it to support any rotation. Okay. And so in the end, you know, I know that node 4 is fixed, and in the end, we're going to just cancel out that row in the matrix. But, you know, I do want to talk about, you know, when you do mix different elements like this, make sure that you pay attention to, you know, what kinds of displacement that node can support. Okay. And so in this case, since we have a node that's just purely connected to the spring, then we don't have to worry about any rotation there because the spring can't support rotation. Okay. All right. Any questions on this? Okay. All right, so let's start putting together our global system. So our global system here is going to be 7 by 7. Okay. And just like before, I'm just going to kind of box the entries. Okay. All right, so let me label all of the columns here. All right, so starting from the top here, we're going to have U1y, then theta 1, then U2y, theta 2, U3y, theta 3, and finally U4y. Okay. And then for the rows, we have all the same things. Okay. And so now let's box the entries where, you know, all the elements are going to act. So let's start with element A. Right, so element A is a beam element and it acts on nodes 1 and 2. And so we're going to box all of those guys together. Okay. All right, I need to go down a bit more. Because theta 2 goes down all the way down there. Okay. All right, so that's element A. Now we're going to do element B. Okay. And so element B is going to be nodes 2 and 3. And so we're going to do all of the degrees of freedom associated with that. Okay. And so that's element B. Okay. And then finally we have element C, which is our spring, right? And so our spring, it acts on nodes 2 and 3, but remember, the spring is not going to interact with the rotation at all, okay? And so it's only going to be acting on the U3 box, okay? So that's going to be right here. Okay. And then we're going to do the U3, U4 box, and so that's going to be right here. And then the U3, U4 block, which is down here. And then the U4, U4, which is in the very bottom corner right here. Okay. Right. And then everything else in this matrix we know is going to be zeros. Okay. All right. And so just like before, you can go ahead and fill in all the entries in this, in the matrix according to your element stiffness matrices, okay? Here you have to be careful though, because, we have two different element types. And so don't forget that for the beams that we have our coefficient in front of EI over L cubed, okay? And so make sure you're punching those into your calculator correctly, because then once you apply the spring, the spring doesn't have that EI over L cubed out in front, okay? Because the spring is just K. And so make sure that you account for both of those, once you're filling in the matrix. Okay. All right. So any questions on the assembly? Okay. All right. And so now that we've assembled the matrix, now it's time to apply boundary conditions. But since this problem is going to ask us to solve for the reaction forces, don't throw this matrix away, okay? And so at this point, the matrix is, we've included all the element stiffness matrices. We just haven't applied the boundary conditions, but we're going to use this same matrix here to compute the reaction forces. So save this matrix. Okay. Okay. Because that'll just help you, that'll just save you some time in the long run. Because if you kind of modify this matrix and then you see the problem asks you to compute the reaction forces, you're gonna have to write down the entire matrix again. So just to kind of save you some work, save this matrix, maybe take a picture of it or something, so that or even better, do this in MATLAB or Excel, just so that you have all the values there for you. Okay. All right. So now let's apply the boundary conditions. And so the boundary conditions, we know on node 1, we have a fixed support. Okay. Okay. All right. So and that tells us that both U1y and theta 1 are going to be equal to 0. Okay. Right. And so we're gonna go ahead and apply that boundary condition here. So we're gonna have 1, 0, 0, 0, 0, 1, 0, 0. Okay, and everything else is zeros. Okay. And then the other boundary condition that we have is that node 4 is kind of fixed into the ground. Okay, and so we don't have theta 4 here because node 4 was attached to the spring, but we do have U4y. Okay. And so we're going to turn that row into all zeros and a 1. Okay. Right. And so once you do that, you can go ahead and plug in all the numbers for this and compute all that. And then we also need to apply our load. Okay. And so in this case, we just have one load, and that one load is being applied onto row U3. Okay. And so when we write out the right-hand side vector, it's going to look like this. Right. And so we're going to have zeros for the first 4 rows, then a minus p for the vertical load, since that vertical load is acting on node 3, and then zeros everywhere else. Okay. And then once you have that system, you can go ahead and plug in all the numbers, and then you can solve it in MATLAB.
Do you have all, I mean, I know you probably won't do it right now because it's too tedious, but do you have the empty spaces for the rest of it, for the green?
Yes,
The
yeah.
red.
So it's all in the lecture notes. So they it's all filled in for
Okay.
for that. So if you look
Thank
at it's lecture notes 4, and it's at the bottom of page 7 of that lecture notes. All right. So any questions on this before we go ahead and solve it?
So in this example, you just applied the boundary conditions before doing the assembly?
I did it after the assembly. So when I say assembly, that part is taking all the element stiffness matrices and putting it into one system. And so that's assembly. And then boundary conditions take place after that. And then after you apply the boundary conditions, then you solve the system. Yeah.
Okay, I see. Thank you.
Mm-hmm. Right. Okay. And so after you plug in all the values and then you solve for it, you get the following solution. And so you're going to have seven things your MATLAB is going to spit out for you. Okay? Right, so first you're going to have U1y and theta 1. And so these guys are just going to be zeros because they're at the fixed support. Okay. And you get 0 meters and 0 radians. Okay. Oh yeah. So when you do solve these in MATLAB, the number that you get for the rotations, those are given to you in radians, okay? So it'll give you a number, but the units for that is radians. All right, and so U2y here is going to be minus 0.02 meters. And then theta 2 is going to be minus 0.012 radians. Right, U3y is going to be minus 0.0638 meters. And then theta 3 is going to be a minus 0.016 radians. Okay. And then U4y is just going to be 0 because it's fixed into the ground. All right. Right, so now that we have our displacement solution, we can go ahead and plug this back in and solve for the reaction forces. Okay, and so the reaction forces are given by the following. And so, remember, we're going to have our global stiffness system before we apply the boundary condition. So this is the step right after assembly. Okay, it's after assembly, but before boundary conditions. Okay. And then to this, we're going to multiply our vector of solutions, which we just found. And so it's going to be U1y, theta 1, U2y, theta 2, U3y, theta 3, and U4y. Okay. And this gives us all of the forces at all the nodes. We have F1y, M1, F2y, M2, F3y, M3, and F4y. Okay. Was there a question on this?
Yeah, Professor, I have a question.
Sure. What's up?
So in the case of the spring, the K, would you multiply times EI over L cubed, or where would the K go?
Yeah, that's a good question. So the K, the element stiffness matrix for the spring, we don't have the EI over L cubed, right? And so to kind of cancel that out, what you'll see in the notes is I have this right here. So you have K L cubed over EI. And so this will basically cancel out with that coefficient out in front, and then you end up with just K. Yeah. Another way to kind of get around this is to just simply plug in all the numbers for this kind of ahead of time. And so if you kind of have numerical representations of the element stiffness matrices, then you don't have to worry about or fussing with the symbols there, because all of it will be in numbers already. So that's actually what I would recommend for these ones. Is just to do the calculations first, get everything in numbers, and then plug those into the matrix kind of directly. Yeah.
Okay, thank you.
Mm-hmm. Okay. And so after that, we can, if we perform this multiplication, you get the following. To get F1y is equal to 37.23 kilonewtons. Right. M1 is equal to minus 893.62 kilonewton meters. Right. Remember, these are non-zero because these are at the supports, right? So that's why we get something there. Okay. Whereas both F2y and M2 are equal to 0, because that's, there's those nodes aren't being supported and there's no loads there. Okay. And so then we have F3y and M3. So F3y is not 0. So F3y is going to be the load, because that's what we're applying there. Okay. And then M3 is equal to 0 because we don't apply a moment there. And then F4y, which is the reaction force from the ground, is going to be 12.77 kilonewtons. Okay. Right. And again, we have a reaction force there because that's where we're applying a constraint. Okay. All right. Any questions on any of this before we wrap up for today? Okay, so that's all we got time for today. So thank you guys for tuning in. And so on Tuesday, we're going to finish up these lecture notes and talk about distributed loading. Okay, so distributed loading is a very important topic because a lot of times that's how we model the loads. And so how do we take a distributed load and put it into a finite element context? That's going to be the subject for the next lecture. Okay, and so have a great weekend, everyone. Thank you guys for tuning in as usual, and I'll see you guys on Tuesday.
Thank
So
you.
we're
Have a
going
nice
to be
weekend.
using,
Professor.
Thanks, guys.
Thank you.
Wait,
So
Professor,
are
what
we
did you say? Sorry.
So are we going to be using ANSYS for the next session?
No, so ANSYS, our next ANSYS session is going to be in week 6, actually.
Okay.
So next week, because I want to time it such that the ANSYS activity is kind of due after the midterm, and so that's why I kind of want to wait until then. So I think next week we'll finish up beams, and I think we'll start kind of the our lecture notes on strong and weak forms, which I think probably will be more interesting just because probably you guys haven't seen those before. And then we'll do the activity, and then it'll be due after the midterm. Yeah.
Okay. Thank you.
Yep.
And Professor, what did you say about F3Y?
Yeah. So F3Y here, remember, node 3 is where we're applying the load, right? And so the load value here is 50 kilonewtons. So I didn't have it in front of me, so I didn't see what it was. And so F3Y, when you compute the reaction force there, it should be minus 50 kilonewtons.
Oh, I see.
Yeah,
Okay.
because that's the load that we're basically applying. So you can almost think of it that's the force that node is experiencing.
Right. Okay. Thank you.
Mm-hmm.
Professor.
Hey.
So the displacement solution that we got all negative values, right?
Yeah.
So the theta was in this negative, it's counterclockwise, or no, it's actually clockwise, correct?
Right. Yeah. So the standard that I use is counterclockwise is positive radians and clockwise is negative radians.
Okay. So so that means like the the spring isn't strong enough for that load, right? Because actually, if it was meant to sustain it at equilibrium.
Mhm. Right. Yeah. So the spring is going to compress a bit, and so it's definitely not as strong as like a a pin support there. So it's supporting it a little bit, so it's preventing it from totally displacing like that, but it's not strong enough to really prevent it from displacing. Yeah.
Okay. Thank you.
Mm-hmm. Do you guys have any other questions? Okay, so I got to run to another lecture, so I'll see you guys next week.